Hello, my name is Alexander Madrigal, and I will be explaining code for independent weighted random query sampling with colors using KD trees. So the basic idea is to randomly sample points with weighted colors using a query and have all points randomly selected be independent of the query, meaning that if the query does not change, all points will be randomly selected. This deviates from code 2, which is the same problem but has dependent query range, where given the same query range, it will always return the same point, but code 4 is different, where if the query does not change, it will return a random point. So this is the procedure. For each color, we will create a sorted list in increasing order, as well as a 1D range tree for each color. For each point, um, for all points in all the colored list, we will insert a point, x and y value, into a 2D list, where the x value is the value of that current point, and the y value is the predecessor of that point, where if the smallest point in a list, the predecessor is negative infinity. Then we will build a KD tree using that 2D list of points. And then we will find the canonical set using a query range, where on the x dimension we will do x min, x max, and on the y dimension we will do negative infinity to x min, not including a negative infinity and x min itself. Then from the canonical set, we will select one canonical node with probability based on its weight of that canonical node. And then, since we have guaranteed that each canonical node has, each point in the canonical node has a unique color, we will randomly traverse a canonical node and select a leaf node based on the weight of its children. And then finally, given uh, a node that has a unique color, we will look at the one-dimensional range tree of that associated color and print a uniform random node. So I will briefly explain why this implementation works. So the basic idea is we must first find a weighted random color, and from that weighted random color, we can find a uniform random node in a range tree that only contains points of that color. So the first job we need to do is find that weighted a list of all colors within the query, and to do that we need to transform our one-dimensional points into two-dimensional points, where for each color a point is its x value is its current point value, and its y value is the predecessor of that point. And if the point is the smallest point of its respective color, its predecessor is negative infinity. And this query, when we run this query range, this y range, negative infinity to x min, guarantees that there is only one point of each color in the final query range. So once we run the query range on our KD tree, there each point that is satisfied in the query range, there will only be one at least at most one point for each color. So there is impossible that there is more than one point of each color, and this is since the second condition, negative infinity to x min, guarantees that the only point that satisfies the condition is the smallest point of its color, since it is the only point where the predecessor is smaller than x min. And since now that we have a canonical set of our points within the query, we can find a canonical node, and from the canonical node we can find a leaf, which is a unique color, and then from that unique color we can simply run a uniform random search on the range tree of that specific color, thus returning a uniform random point with weighted colors that is independent. So now we'll explain the implementation. So we have two classes right here. We have a bounding box, which we will use to run the query with x min, x max, y min, y max, defining a box. Then we have a node with a color, an x value, a y value, a left node, a right node, a weight, as well as a box. Then we also define a getX and getY, which simply returns X value and Y value respectively, and this will be used because of sorting. And then we have our one-dimensional range tree functions, which are build range tree, find split node range tree, find canonical set range tree, and then finally uniform random node range tree. These are the same implementation as code 1, where we find a uniform in a range tree. So please look at that code if you want an explanation of these functions. But like I said previously, we need these one-dimensional range tree functions because for each color we will be building a range tree, and we will need to select a uniform node from that range tree for each color to actually return a point. Then we move on to the actual implementation of making our KD tree. So two things that we will need to use is a color weight dictionary as well as a color strict dictionary. So the color weight dictionary, which is passed in the constructor, will simply have colors paired with the color's associated weight, so we can use the weight of that color. And then we will also create the second color, this color struct dictionary, which will have colors associated with either a colored list or a colored range tree, and we will change that as we go. So the first step is to transform all of our points into two-dimensional points, P and P predicate P. And so what we'll need is we'll need the list of points, and we will return our transformed list. So first what we must do is we must append points into the color dictionary. So for the respective color, if that color is already within the dictionary, we will append our point to that list. And if our color is not within the dictionary, we will create a list on that point for that respective color. Now, what we'll do is for each color, we will access its associated list, and we will sort the list in ascending order. So now the dictionary has colors paired with a list of points in ascending order. So now we can start assigning each point predecessor y value. So what we'll do is we will iterate through the entire list for each color, and for the very first point, since it's sorted in ascending order, the very first point is the smallest, so its predicate or y value will be negative infinity. Otherwise, the point's y value will be the previous point's x value. And then we will simply append our point, our two-dimensional point, to the transform list. So at the end, our transform list will contain a list of all two-dimensional points for all colors. And then at the end, we will return that transform list. But what we want to do first is, since we no longer need the color dictionary, the color struct dictionary, to contain lists of points in ascending order, we can now transform it to contain the range tree. So using the list we have created, we will build a range tree using the build range tree function, and we will simply assign each color's dictionary to that associated range tree. So now our color struct dictionary has colors paired with range trees. And then finally we can return the transform list. So now we can start building the KD tree. So what we need is the list of transform points, which we just built, the depth of the tree, as well as the bounding box of the root node. So at the start for our root node, when we don't pass anything as a parameter, we set our depth to 0, and for the root node, the bounding box is simply the bounding box or the range of points. Remember, this is the transform points now. So it will have a x min, x max, y min, and y max. And we will sort using the get x and the get y functions respectively. Now, we move on to the base case, where if P just has 1 point, we are now a leaf node. And so we will create a point of its respective color, x value, and y value. Its bounding box is just the bounding box of its parent, and its weight is simply the weight of its color. So we will use the color weight dictionary where we can input its color and it will return us the numerical weight of that parent node. Then we move on to the recursive case where we will split our range depending on the x and y value. So this will be determined on whether the depth is either even or odd. So when the depth is even, we will split our bounding box on the vertical direction and split it on the x median. So what we'll first do is we'll sort our list of points in the on the x dimension. Then we will find the median x value, and using the median x value, create a left list and a right list. So we will create a node that has the value of the median x value and set its box to it associated, assign its associated box. But then we must recursively build its left child and right child. So what we'll do is we'll have its list be for the left child will be its left list, its depth will increase by 1, and its box will be left box, which I'll explain in a second. For right, it is very similar, where we build recursively call it on the right list, increase the depth by 1, and call it on the right box. So how the box is changing is for the parent node, we are splitting the box on the median value, meaning that the upper and lower bound for the y's does not change at all, but the range for the x values does change. So for the left box, the minimum value is the same as the parent's box, but the y value is now the median value. And then for the right box, the minimum value is now the median value, and the maximum of the box is the same as its parent. And the node's weight is the sum of its children's weight. And so we'll do the same thing on when we split on odd depth, but instead now we're doing the y dimension, the splitting on the y median value. So we'll find the y median, find the left and right list, create a node on the median y value, assigning its box. Then we will create a left and right box for its left and right child. So the left box, for the left and right box, the upper and lower bound for the x is exactly the same, since it remains unaffected, since we're only splitting on the y median value, but the y ranges will change. So the left box, the minimum will remain the same, but the maximum is now just the median value. And then for the right box, the minimum value is the median, and then the maximum value is unaffected from its parent. And then likewise, the weight will be the sum of its children's weight. And then finally, we'll return the root node. So now, given our um, given our KD tree and our query range, we want to be able to find the list of canonical nodes that satisfy the query range. So first, what we need to do is we need to transform our one-dimensional query interval, which is xmin xmax, into the two-dimensional bounding box xmin xmax times negative infinity xmin. So what we'll simply do is if the min and max are not, y min and y max are not set, we'll set y min to negative infinity and y max to x min. And we also initialize the list of canonical nodes. So at the base case, if our root is a leaf, we will check if the root's point intersects the query range. So if the x value and the y value is in between the queries xmin, xmax, as well as the queries ymin and ymax, that means that our root node is a canonical node, and thus we will append it to C. Then, if root is not a leaf, we will have to run some checks to see if it is a check if the root is a canonical node or not. So, if the root's bounding box does not intersect Q at all, that means that the root and its left and right children will not be within the query at all. So we can simply return C and stop this path. Then, if the root's bounding box fully intersects our query, meaning that the roots box is fully within the query, that means our root node and all of its left and right children are within the query, meaning that our current node is a canonical node. So we will append it to the root. And we do this simply by checking whether our xmin, xmax, and ymax are within the query range, and that means we are a canonical node. And then finally, we will check if our roots box partially intersects Q. And what we must do if we partially intersect is we must traverse the left and right, recursively traverse the left and right children. So we'll call our query KD tree on the left and right. And what we'll do is we will add the canonical nodes on the left side and the canonical nodes on the right side to C and return C, which will give us a list of canonical nodes. So now that we have a list of canonical nodes and a query range, we want to be able to return a weighted random color node. So what we'll first do is we must first pick a canonical node from the list of canonical nodes. So we need to find the canonical node with the highest key based on its weight. So what we'll do is we'll assign the first canonical node to Cmax and find its key, which is a random number 0 to 1 to the power of 1 divided by that node's weight, which we'll find using the color weight dictionary, using the node's color. Then we will iterate through the rest of the canonical nodes, finding its key and comparing its key to the max's key. And if our current canonical node's key is greater than the current maximum key, we'll assign our current canonical node to Cmax and our current maximum key to the current key. And at the end, that will mean that we will have a canonical node with the highest utility. Then from there, we want to traverse that canonical node until we reach a leaf node. So what we'll do is while our node is not a leaf, we will compare the keys on the left and right children and traverse the side with the greatest key. So we'll check if the left key is greater than the right key. If it is, we will traverse the left side. Otherwise, we'll traverse the right side. Now, finally, at the end, V will be equal to a leaf node. And this leaf node is a unique, remember that each leaf node from the list of canonical nodes is a unique color. So V now is a point with a unique color. So now from that color, we need to find its associated range tree and pick a point from that range tree. So we'll find the canonical nodes in the one-dimensional range tree of that point's specific color, as you can see here using the color dictionary, and then we will return a uniform random node range tree using that canonical nodes, and thus we have finished the problem. So just some testing that we ran. We initially did it with a database size of 1,000, as well as having 6 colors, where we randomly assigned points to random colors. Then, after creating the class, finding the two-dimensional points, building the Quady tree, defining the range, finding the canonical nodes, and then finally finding a random node, we can return a random node's value and color. And then finally, down here, we have we want to verify that we are actually returning points with probabilities associated with its color. So we want to check the distribution of selected colors when we run random nodes. So iterating it 10,000 times, we will find a random node and depending on its color, append it to a frequency list where we can finally see the percentages that each color is being selected. And then down here, we simply have a code that also runs 10,000 times and selecting a random node. And what it'll do is it'll find the X min and X max and see what the range is. So if I run the code here, we find a random node, which is 451 blue. We have a frequency of colors. So our actual frequency of colors is this right here, and our theoretical is this right here. So as you can see, it is relatively close to the frequencies. And then we have the range of random nodes, which is exactly the same. So thank you for listening.